Thank you very much. Okay. Thank you very much, Katja and Knut, for the kind invitation to give this talk. So the talk is about the minimal surface transformation. I will, of course, explain what it is. And this paper is based on a preprint from last year by me, Leonard Busch, Mikko Salo, and Leo Zhou, which was called Generalized Boundary Rigidity and Minimal Surface Transform. Just a second, something. Okay. Now it is. Okay, so here's the outline of the talk. So it goes as follows. I will start with introduction and tell you what is the generalized boundary rigidity. Then I will go to earlier results and how these results are obtained. They are sort of by this PD approach. I will tell you what it is. After that, I will go to this new approach, which is the topic of today, which is this integral geometry approach and how it leads to this minimal surface transform. After that, I will go to main results, what we obtained in the paper, which was mentioned in the opening slide. After that, I will actually go to a sketch of proof. How do you prove the injectivity of the minimal surface transform? There are a couple of things which I would like to explain in the proof, which might be helpful in other problems as well. And in the end, there's a summary where I will compare this PD approach, the Calderon, and this integral geometry approach, the Radon. So let's start. So let's first recall what was the classical boundary rigidity problem. It asked if one can determine a Riemannian manifold with boundary up to an isometry from the distances between the boundary points. So you can move these boundary points x and y on the boundary, and you're allowed to measure the distance d, x, y between those ones. And here the distances are lengths of geodesics, so the minimizers of distances are geodesics, and you know the distance between boundary points. This was conjectured by Michel in 1981, and then there's a beautiful paper by Best-van Uhlmann 2005, and they proved the conjecture for simple two-dimensional manifolds. Then some other beautiful papers for generic simple metrics. It was proven by Plamen, Stefanov, Günther Uhlmann, Plamen and Günther in 2005. And then after that, there's a large gap in the time. So there was local and global results under foliation condition by Plamen, Günther, and Anders Wasu a few years back. This classical boundary rigidity, it's closely related to the study of the invertibility of the X-ray transform. So X-ray transformation integrates a function over geodesics. Okay, so what is generalized boundary rigidity? So now in this generalized boundary rigidity, we ask if manifold Mg is determined by areas of minimal surfaces instead of lengths of geodesics. I will define what are minimal surfaces, but you can think about that minimal surfaces are higher dimensional generalizations of geodesics. And here the minimal surfaces, they start from the boundary of M. So they start from the boundary of M, they span inside. In fact, this generalized boundary rigidity, it has been considered by physicists for the past 20 years. And this started from this ADS-CFT correspondence, and especially by this Rui-Takayanagi proposal from 2006. I will shortly discuss this a little bit later. The first mathematical results in this context were by Spiros Alexakis, Tracy Balehowski, and Adrian Nachman, who is in the audience, also from a few years ago. The minimal surface transformation, it generalizes the X-ray transformation. It integrates a function over a family of minimal surfaces instead of integrating function over geodesics. And similar to the classical boundary rigidity, we will see that the generalized boundary rigidity is closely related to the invertibility of the minimal surface transform. So what are minimal surfaces? Let's define them. So minimal surface is a surface that locally minimizes area. Equivalently, this means that its mean curvature vanishes identically. And as I said, minimal surfaces are higher dimensional generalizations of geodesics, which are in fact one-dimensional minimal surfaces. If you consider situation Rn, there a surface which is given as a graph of function u is a minimal surface if and only if the following equation holds. So here you see, can you actually see my pointer? Yes, you can. Here this equation is divergence form equation of the form nabla dot gradient u divided by this square root of 1 plus gradient u squared. As an equation, this is quasi-linear elliptic PDE, and you can solve this equation for a given boundary value f. If you linearize this equation, you will get, if you linearize that at the zero solution, so you give boundary value 0, then the solution is 0, and if you linearize that zero solution, you will get just the Laplace of Rn. So I put here some examples because they look nice. So classical minimal surfaces, they have been studied for a long time. In R3, they include catenoid, helicoid, and a little bit maybe less known is this Enneper's surface, but these are all very old findings. So even this Enneper's surface is from 1864. And here below are some more exotic examples. The first one is called Scherk's doubly periodic surface, and the second one is called Shane's triply periodic S prime surface. Don't ask where the name comes from, but they look like such in the pictures. So they're smooth, but they look quite complicated. So what I want to say is that the class of minimal surface, even in R and R3, it's very like there are a lot of those. It's very broad. I must mention here that these images are from this minimal surface.blog. It has a nice collection of various minimal surfaces. If I take a look. Okay. So I mentioned that this generalized boundary rigidity is motivated partly by physics. And there was a so-called ADS-CFT correspondence. It was proposed by Juan Maldacena in 1999. And it aims to unify quantum mechanics, which is conformal field theory, or CFT in the name, and general relativity, which is anti de Sitter spacetime. It is this ADS, CFT. And this is a hugely popular topic in physics. So in fact, this Maldacena's paper, it's the most cited paper in physics ever. It has something like 30,000 citations. It's a huge field. And to be honest, I don't know what's going on in the paper. It's just complete magic to me. Anyways, so there was then this refined, or like one specific proposal some years after Maldacena's paper by Rui and Takayanagi, 2006. And it says the following. So I will first read the statement of this proposal and then explain what it is in more detail. So in words, it says that entanglement entropy S of a boundary region omega equals the area of a minimal surface in the bulk that is anchored to the boundary of omega. Okay, so what this means is that consider a manifold with boundary. You can think about that the manifold with boundary is just a solid ball if you want. On the boundary of this ball, which is now a surface, is the unit sphere. There's a boundary region omega. So omega lives on the boundary of the manifold. Then in physics, you can compute the entanglement entropy relative to this omega. So this omega, it splits the boundary to omega and its complement, and the entanglement entropy, it measures the quantum correlations between this division of the boundary. On the other hand, this omega itself has a boundary, And you can span a minimal surface which goes inside. It goes inside the solid ball from the boundary. You can start the minimal surface which is attached to the boundary of omega, which goes inside the manifold. So this sigma omega is a minimal surface, and it lives inside this manifold, which you can think about to be a solid ball. And then you can compute the area of that minimal surface. And the Rui-Takayanagi formula is that this entanglement entropy is this area of this minimal surface defined by this omega divided by this Newton's constant Gn. Then in physics, of course, they ask that can we invert this relationship? Namely that given entanglement entropies for all omegas living on the boundary, can you reconstruct the bulk geometry? So think about what this means through this proposal. So if you know the entanglement entropies for all omegas, then you know areas of all minimal surfaces which span inside of the manifold. So this question really asks, given all areas of minimal surface, can we reconstruct the bulk geometry? But this is precisely a generalized boundary rigidity problem we discussed in the earlier slides. In physics, they call this bulk reconstruction. So let me then get to earlier results on this generalized boundary rigidity and the so-called PD approach, what I call PD approach to the problem. So earlier results on the generalized boundary rigidity are mostly based on methods for the Calderon problem. Here below, I will explain what I mean by that. And I will work in Fermi coordinates x and t. So I will have surface, sigma. Here sigma can be minimal or not, but it's a surface. And I have a point there, and then these Fermi coordinates x and t, they shoot geodesics from this x, and this t is the distance to x. So x lives in n-dimensional space, so this xt is in n+1 dimensions. I will also abbreviate this gux as gxux. By definition, minimal surfaces, they are critical points of the area functional. So now consider that your minimal surface is given as a graph of a function u. Then in Riemannian geometry, so now we are in the Riemannian setting, the area of such graph is given by this formula au here. So it integrates over sigma, this quantity where you see two square roots. These minimal surfaces are the minimizers, at least they're extremal. It means that if you vary this area functional through u, keeping the boundary value of u fixed, then the calculus of variations will give you the extremizing equation, the equation of motion, if you will, Euler-Lagrange equation, if you will, which is the minimal surface equation given here below. So this minimal surface equation in general Riemannian manifolds, it has two components. The first component is sort of like a Riemannian version of the minimal surface equation in Rn, which we saw in the earlier slides, but it also had this additional component f u gradient u. So it's a term of u and its gradient. But we don't need to worry about this exact form of this equation in this talk. But it looks like that one here. Okay, so that is what you get when you vary this area functional through boundary fixing functions. You can also vary the area functional through minimal surfaces themselves. So consider now a one parameter family of minimal surfaces given as graphs of function u epsilon. So u epsilon, we give it boundary value f plus epsilon v, and then we differentiate the corresponding areas of these minimal surfaces. Then after some computations, you will see, and using the fact that each of these u epsilons correspond to minimal surface, you will see that you will get a boundary integral of the function v in u epsilon against the DN map applied to the function f, where the DN map is the Dirichlet-Neumann map of the minimal surface equation we saw in the previous slide. So what does this mean? Well, it means that if you know areas of all minimal surfaces, it means that you know these AU epsilons. Especially you then know the area, you know the epsilon derivative of those AU epsilons, which means that you know this left-hand side. But note now that this function b here is freely chosen. So it means that you, from this left-hand side, you can choose b freely. It means that you actually get this DN map applied to this arbitrary f. So now we have this important equivalence. Knowing the Dirichlet-Neumann map is equivalent to knowing areas of nearby minimal surfaces. So this equivalence now allows one to approach the generalized boundary rigidity either through what I call PD methods, so focusing on the DN map, so you take the DN map lambda here and try to get information from that, or as we see today, you can also analyze the area function directly. So we will do this latter approach today. Let me then get to earlier results, and these are based mostly on analyzing this Dirichlet-Neumann map of the minimal surface equation. So in this slide, all of these results are based on the DN map analysis. So as I said, this is an original paper by Alexakis, Palehovsky, and Nachman, 2020. And this was the first rigorous mathematical result in this context. And it says the following. So let Mg be a three-dimensional manifold, which is homomorphic to a ball, and assume that it satisfies certain curvature assumptions and that it's also foliated by minimal surfaces. In this case, the areas of minimal surfaces, which are topological disks they actually uniquely determine this manifold completely. So this solve the boundary rigidity under these assumptions in dimension 3. Then after that, 2024, there was a paper by Katalin Karstea, me and Leo Zhou, where we focused on recovering minimal surfaces themselves. So this paper recovered two-dimensional minimal surface sigma. There's always an isometry here, so up to an isometry from the areas of minimal surfaces. So this is a general result that it assumes no topological curvature or foliation assumptions on sigma or the ambient space, but it only recovers the minimal surface. Minimal surface is not the full bulk metric. Other results, there's a paper by Katalin, Matti Lassas, me, and Lauri Oksanen, where we studied this toy model. So this toy model is a cylinder. The analysis is quite simple. Some papers by Janne Nurminen from 22 or 23, and he was able to recover Taylor series of conformal factor of the metric in certain situations. And let me also mention a paper by Sebastian Munoz-Ton, 2024, where he studied the Calderon problem for harmonic maps. Harmonic maps are also generalization of geodesics. But the common factor of all of these results is that there is actually two results. In one way or another, they rely on solution to the Calderon problem. They all use CGOs in the arguments. Some other works, and these are now in asymptotically hyperbolic settings. So this ADS-CFT, the holographic proposal, there the bulk, the manifold, is asymptotically hyperbolic. It means that the manifold is infinite and it has certain behavior at infinity. Examples of these asymptotically hyperbolic manifolds are time slices of this under de Sitter spacetimes. And here the minimal surface stays stretched to the infinity, which is called the conformal boundary at infinity. Physics literature on this bulk reconstruction is the physics term for this generalized boundary rigidity. Here are just few, there are a lot of others, by Ningbao, Samuel Wilson, Junjun Kao, Sebastian Fischetti, Veronica Hughes, Cynthia Keeler, Arttu Pönni, Javensun, if I remember correctly. These are varying levels of rigor. And let me also mention that the physicists are already quite far into business in the sense that they try to use machine learning for this bulk reconstruction. Okay, so those are the physics results. Minimal surface which go to the infinity, so they naturally have infinite area. And for that reason, one studies the so-called renormalized area, which is some kind of like a normalized version of the area of these infinite surfaces. And there's a nice paper by Jared Marx-Kuo from a couple of years ago, and he studied the inverse problem for renormalized area of minimal surface in asymptotical hyperbolic manifolds. And he was able to recover the conformal infinity and asymptotic expansion of the metric. So that basically means the boundary determination at the infinity. And especially when the manifold, the bulk, is analytic itself and topologically trivial, then he was able to recover the full manifold. Let me also shortly mention this paper by the physicist Niko Jokela, Miika Sarkkinen, who is an ex-physicist, nowadays a mathematician, me and Leo Zhou, and this was published in a physics paper, Journal of High Energy Physics. And there we studied a time slice of asymptotically de Sitter space-time metrics in hyperbolic half spaces. So the metric form is given here, and the unknown is this f. And what I want to say from this result is that we were actually able to derive an explicit inverse of formula relating the entanglement entropy variations to bulk metric deviations. So in mathematical language, this means that we were able to solve the linearized problem explicitly. And the nice thing about this paper was that it actually improved the state of art in physics. So the inverse mathematics was here able to advance physics. So that was pretty nice. Yeah, we recovered the Schwarzschild black hole at low temperature to first order. And finally, before we go on, let me also mention a related result by Alberto Enciso, Günther, and Michal Brockna from last year, where they studied the DMAP for the wave equation on asymptotically ADS space times. So now we have some motivation for the problem. So let's go on. Okay, so those were based on the, apart from this, maybe this Jared's paper, those were based on analyzing the DMAP of the minimal surface equation. So let's then go to this new approach, integral geometry approach, and how we get to this minimal surface transformation. Recall from the earlier slides where we did this calculus of variations. We realized this equivalence. So knowing the DMAP is equivalent to knowing areas of minimal surfaces. So now, instead of working with the DMAP, this PD approach, one can start to study the area functional directly, which I call the Radon approach. As we will see, if you linearize this area functional in the metric, so in the unknown, this will lead to the minimal surface transformation. And let me now get more details in this setup. So let me define things more carefully. So we have manifold M, which is compact, it has a boundary. Dimension is general, the dimension is n plus 1. And we put this M inside a slightly larger manifold M tilde. And I denote it's the metric of M tilde still by G. And then I fix a minimal surface, sigma, which is suspended from outside of this M. So this is for technical reasons. The boundary of sigma is in M tilde minus M. So M tilde is bigger than M, and sigma lives inside M tilde. The minimal surface transformation, I can formally define it as follows. We need to refine this definition for a certain reason, which I will go next, but let's take this formal definition first. So let M tilde G be a Riemannian manifold, let S be the set of all compact, smooth, embedded minimal surfaces inside M tilde with smooth boundary. Then the minimal surface transform is the operator which takes a function beta inside m tilde to r beta. And now you need to think about what is this r beta. So it's sort of like a functional. So if you give r beta a minimal surface, it will give you a number, which is the integral of beta over the minimal surface. So it's sort of like a functional. It's not a linear function, but it's sort of like a functional. Well, some features, obviously, it integrates a function, beta, over a family of minimal surfaces. And next we go to suitable parameterization for this S. So after suitable parameterization, this minimal surface transform belongs to the class of Guillemin's double vibration transforms.
So Tony had a question here. These minimal surfaces, I mean, they could be occupying, like, I'm trying to think of, let's say your M tilde is a manifold times R, like let's say, n plus one dimension. And these minimal surfaces are like, could be just a very small part of over M or something, or do they extend all the way to the edge or something? So
Yeah,
what do you know about all these minimal surfaces for these manifolds?
yeah, thanks for the question. I need to go to specific definitions, what we need is in this theory. I will go to that in a little while. There it is. Well, let me go to there, but thanks. I will explain it in a short while. But before we can go to any analysis of this transformation, we need to give a parameterization for these minimal surfaces, which is this set S. So unfortunately, unlike for geodesics, which you can parameterize, for example, by unit sphere bundle, so points xv in this Sm unit sphere bundle, there actually is no global simple parameterization for minimal surface in general available. So for this reason, we work near a fixed minimal surface. So we fix a minimal surface at the beginning. So let now sigma be a fixed minimal in this m tilde g. Then I can consider variations of this sigma. So how do I do that? So I solve the minimal surface equation for given Dirichlet data f. So f is small Dirichlet data. I solve the minimal surface equation. This will give me a graph over this fixed minimal surface sigma. So this gives me a family of minimal surfaces which are parameterized by the Dirichlet data f. Okay, so now we can parameterize this minimal surface somehow, at least locally. With this parameterization, I then define the area measurement operator. So this W is a small neighborhood of 0 in the boundary value functions. And the area measurement operator is the following. So you give a Dirichlet data, consider the graph sigma GF, and then you get the volume of that sigma GF. So the metric is now fixed, and then you solve the minimal surface equation and you compute its volume or area. So this is the area measurement operator. So now we have a local parameterization for the minimal surface, and we can start to do analysis. Okay, so notice now that the inverse problem, the general boundary rigidity, is to invert this map. So a metric gets mapped to this area functional area G. And we study this inverse problem now by linearization methods. So for this purpose, let's now fix a background metric G0 inside M tilde and consider conformal families. Consider conformal metric G, which is conformal factor alpha times this G0. And for notational purposes, let me also just denote area alpha functional to be the area functional of alpha G0. Then what happens is that if you differentiate this area functional in alpha, it is precisely differentiable by some standard methods. If you take this difference, if you differentiate that alpha is 1 to direction beta, then after computations, you will see that this linearization at alpha is 1 to direction beta is integral of beta over minima surface in the metric T0 with Dirichlet data F. So this is important. So what this means is that the linearized operator in the conformal factor alpha is the minima surface transformation acting on the variation beta on this minima surfaces sigma f G0. So G0 is now fixed, and we consider minima surface parameterized by f in that manifold m tilde G0. So here you can change f, then you integrate beta over different minima surfaces. So this is completely analogous to what happens in the boundary rigidity for if you linearize the area functional there. Okay, so let me then give you a couple of examples of minima surface transformation. So it generalizes classical integral geometry transformations given below. First of all, radon transformations. So hyperplanes in Rn, they are minima surfaces. These are nicely parameterized by vector omega and real number A. And then the radon transformation on hyperplanes is that you integrate over these hyperplanes given determined by this omega and alpha. Then the geodesic ray transformation. So when the minima surfaces are one-dimensional, dimension of sigma is 1, the dimension of ambient space is anything. Then in this case, minima are geodesics, and the minima surface transformation is just the geodesic X-ray transformation. A little bit more exotic, but this also appears in many applications, is this Helgason's totally geodesic radon transformation. So Helgason studied these kind of transformations in constant curvature spaces. And there, the transformation integrates over k-dimensional totally geodesic submanifolds. So it's an integral transformation over k-dimensional totally geodesic submanifolds. But totally geodesic manifolds are always minimal surfaces as well. So also this Helgason's totally geodesic radon transformation is a special case of the minimal surface transform. So let me then get to the main results. And now I'll hopefully ask answer to Rakesh's question. So our main theorem is the determination of conformal factor from the areas of minimal surfaces, and that is based on this condition, which we call ampleness condition. So it says the following. So pick a direction in the cotangent bundle y psi. The condition says that there must exist a minima surface sigma so that this y psi is in the conormal bundle of this sigma. If you don't know what is the conormal bundle, think about that just that y sigma is orthogonal to sigma, the minima surface. So there must be an orthogonal. For given direction y sigma, there must be an orthogonal minima surface. As we will see, this actually means that the manifold M, the ambient manifold, this n plus one dimensional manifold, can be probed in all directions if this ampleness condition holds by minima surfaces. Examples of where this ampleness condition holds, well, subsets of hyperbolic half space, which are timeless ADS spacetime, and also there are, for example, 3D manifolds which admit no closed minima surfaces, and these are results by the big boys in minima surface theory, Laurent Masset, Harold Rosenberg, 2022, Otis Chodos, and Davin Ketover from a few years earlier. So they showed these kind of results that you have this ampleness condition holding. I will, by the way, give the reference at the end of the talk if you're interested in this. Our main result is this one. So let M tilde G0 be an analytic manifold satisfying this ampleness condition. So this G0 is the background metric. and it's analytic. Now, if we consider conformal factors, alpha 1 and alpha 2, they are not analytic. They can, for example, smooth. They are quite close to 1, and they agree outside of this M. So basically, we assume boundary determination. So in this case, if the areas of the corresponding minimal surfaces, it's this condition area alpha 1 G0 equals area alpha 2 G0 holds, then the conformal factors are the same. Moreover, actually, this determination of this conformal factor is even Hölder stable. So formally written, the L2 norm of these conformal factors is bounded by these areas of minimal surfaces with some power gamma. And I don't specify what is the norm there. It's a certain Sobolev norm. So before giving like other results from the paper, let's do a short comparison with the PD approach, which we discussed earlier. So this integral geometry approach, so it magically works actually in all dimensions. So n can be anything over 2. And the assumption was that the background metric is analytic and this ampleness condition holds. So my guess is that maybe you can get rid of this analytic condition somehow, but the ampleness condition is quite natural, and it might not be able to get rid of that very easily. And the stability was Hölder. The earlier results, as I mentioned, they are basically all 2D results. I mentioned these results by Alexakis, Karste, and Nurminen, and others. And the reason why they are basically 2D results is that they rely on the Calderon problem, which is mostly open in dimensions 3. I guess nobody has proven any stability results for this, even in these 2-dimensional cases, but if you do it by the Calderon methods, the stability will be at best logarithmic. So this integral geometry approach really does something different. A couple of other theorems from the paper, and these regard the injectivity of the minimal surface transformation. So the recovery of the alpha from the area data is a nonlinear inverse problem. And as we saw, if you linearize the area data in this unknown alpha, this conformal factor alpha, then it reduces it to the minimal surface transformation and to its injectivity. For the next results, I will assume a foliation condition, which says that M is foliated by minimal surfaces. So this is a little bit simplistic version. In the paper, there's a more general foliation condition. But let's think about this foliation condition for now. So the injectivity results for the minimal surface transform, which we gave, is the following. So assume M tilde G0 is analytic, and either the ampleness condition holds or the foliation condition holds. And we have a function beta, say continuous, which vanishes outside M. And now if the minimal surface transformation of that is 0, then the function is 0 everywhere. So this is an injectivity result for the minimal surface transformation. We also give the microlocal injectivity result, which is the following. So if sigma now is a fixed minimal surface, and if again beta is a continuous function and is an outside, and now here this notation means here that if this minimal surface transformation vanishes for small variations of this sigma, so recall that when you give boundary value f for the minimal surface equation, you get the nearby minimal surfaces. So this condition means that if the minimal surface transformation for nearby variations of sigma vanishes, then the following analytic wavefront set condition holds. So in this case, the analytic wavefront set of beta intersected with the conormal band of sigma is empty. These kind of results are typically called microlocal injectivity results. And in fact, this theorem 2 will be obtained by propagating theorem 3. And I will actually go to that now. So let's go to the proof of this injectivity of the minimal surface transformation. To this theorem 2. How do you prove these kind of theorems? So I will sketch the proof, and then I will tell you what I think are the most interesting things about the proof. So how do we prove it? How do you prove the injectivity of the transformation? Well, the approach here is the following. The first one is to verify the so-called Volcker condition. I will explain that that is sort of the analog of no conjugate points for the X-ray transformation generalized for minimal surfaces. Then we need to also do a reduction in the data space, because now we our boundary values live on function space, so we need to reduct our data space to finite dimensions, and we do that by Runge approximation and by this so-called Whitney projection method. After those points, we will actually get the microlocal injectivity, and after that we will need to propagate this microlocal injectivity to obtain the theorem, to obtain the injectivity of the transformation itself. And before we go to the proof, let me note that the full nonlinear problem, which was the recovering the conformal factor, it actually requires one to compute the principal symbol of the normal operator to the minimal surface transformation. So that is quite a bit more involved proof, but the main ideas are actually in this linearized setup. Okay, so let's go to verify the Volcker condition. So what is that? So first of all, formally, the minimal surface transformation, it fits into the framework of Guillemin's double fibrations. So what is that? So it's this left picture here. So we have the data space. It's this W, that is the boundary values for the minimal surface equation. And then we consider this space Z, which are points of the following form. So you have F in the boundary values, and then you have X on the manifold itself. And the condition is that X must belong to the minimal surface determined by the Dirichlet data F. Sometimes this is called the incidence relation. Why it's called double fibration is that these projections pi W, it fibrates W, and this pi n tilde fibrates n tilde. Moreover, we will consider the graph on the right. So here we have the Konova bundle of this jet, of this incidence relation, and then we have the cotangent bundle of W and cotangent bundle of n tilde. The Volcker condition just says that the left projection here must be injective inversion. So what does that, roughly speaking, means? It means that you can parameterize the guys in the normal bundle of Z by the elements of cotangent bundle of your parameter space. And why it matters? So this is the crux. So when you have analytic double fibration and it satisfies the Volcker condition, then you can control the analytic waveform set of your transform function beta by the transformation. So we want to get to the setup of double fibration satisfying the Volcker condition. Okay. So how do we get the Volcker condition? And I will go now to a little bit details. So these couple of next slides are quite dense, so I hope you don't die when you listen to me. But let me try to explain how do you get that? How do you study the Volcker condition? So first of all, I again work in Fermi coordinates, and I've a little bit simplified the situation. I take the initial, I will take the Dirichlet data to be 0. In that case, the minimal surface is given by T0 in the Fermi coordinates, and the point in Z, in this incidence relation, is this first 0, is F is 0, X is a general point, and when you solve the minimal surface equation for F is 0, you get the 0 solution. So this last 0 is the 0 function of the minimal surface equation. So at that point, the Konova bundle is given by this kind of elements. So lambda is here is a free non-zero number, but otherwise the elements are these ones here. This P here it is the Poisson kernel of the linearized minima surface equation, which I've given here. So Q is the so-called stability operator, and the linearized minima surface equation is just a certain Schrödinger operator acting on B. In the form of this dt is actually conormal to this given minima surface sigma. Okay, so how do you get that? We cannot go to the details, it's a little bit lengthy, but the idea is this one. To get the conormal bundle, which means that it's the set of covectors which annihilate the tangent bundle, you first need to compute what is the tangent bundle. So you need to compute what is Tz here. How to get that is that you consider curves in Z and you differentiate that path at S is 0. So these points belong to the Z, and then you differentiate that S is 0, then you will obtain what is Tz. How to get these elements for this conormal bundle then is that you vary the base point. That will reveal you what is this lambda dt component here. If you vary the Dirichlet data, so this Fs, that will give you this Poisson kernel part of the conormal bundle. So that's roughly speaking how it goes. Okay, now we have the elements of the conormal bundle, and the claim was that this left projection is injective immersion. So that was the Borger condition. So the left projection just takes these first two elements from here. So when you apply the left projection pi L, you just get 0 and minus lambda times the Poisson kernel at x. Okay, here is a reminder what was the Borger condition. It's injective immersion. So especially this pi L needs to be injective. So if we take 2 points from the image of these elements of the conormal bundle, so the left projection just took this 0 and this minus lambda px. So we get the condition that lambda 1, so we have 2 elements. We have lambda 1, x1 in the other one, lambda 2 and x2 in the other, in the second one. We left project these guys. We get that lambda 1 p1, lambda 1 p at x1 must be lambda 2 p at x2. Written differently, it means that p at x1, the Poisson kernel, must be some constant time p at this point x2. And for injectivity, we want to show that x1 is x2. Okay, so how does this work next? So the Poisson kernel means that if you integrate that over the boundary against the Dirichlet data f, you will get the solution to the corresponding equation, which here is the linearized equation, the linearized minima surface equation. So if you take an arbitrary boundary value f, Dirichlet data f, and you do this integration, you will get that any solution parameterized by this boundary value f at x1 must be this constant times the solution at x2 point. So f is here freely chosen. You can choose f here freely. So let's simplify the analysis just a little bit. So assume now that c is actually 1. So in this case, the condition here becomes just vfx1 equals vfx2 for all Dirichlet data f. So it means that all solutions to the linearized equation at this point x1 and x2 must have the same value. So that means this injectivity is equivalent to showing that solutions to the linearized equation QV0 must separate points. Okay. For the minima surface transformation, the Borger condition always holds. And that is based on this Runge approximation. So the stability operator, as I said, the linear operator is just the Schrödinger operator, Laplace plus Q. And for that, you have the Runge approximation results, which says for the following properties. So if you have different points, then there always exists a boundary value, Dirichlet data f, such that at those points, the corresponding solution have different value. Moreover, you can fix the value of the solution, and its its differential at the point x, so that you can find a solution having the value a at the point, and the differential is this given vector xi. But just consider the first one now. So in the earlier slide, we had that this must be equality for all f. So now we can choose f that the equality breaks if x1 is not x2. So it follows that x1 must be x2, which means the injectivity of this pi. So the separation of points by solutions to the linearized equation gives the injectivity of the left projection. The injectivity of the difference of the left projection follows from this second one. So all in all, this Runge approximation gives that the Bolker condition always holds if the minimal surface has dimension at least 2. If the dimension of the minimal surface is 1, so that the minimal surface is geodesic, this injectivity of pi L is equivalent to the condition that the geodesic has no conjugate points. And by this reasoning, the Bolker condition generalizes these no conjugate points to higher dimensions. So this is the crux. Okay, then I mentioned that, okay, now our parameter space, the boundary values, it's infinite dimensional, so we cannot apply any standard FIO for integral operator machinery, and we do a finite dimensional parameterization of this space. So for this reason, we will use this Whitney projection method, which we can use to restrict our data space to finite dimensions. Namely, we can find capital N amount of Dirichlet data, so F1 to F capital N, where capital N is given as 2n plus 2. And by this Whitney projection, actually this VF1 to VF capital N, they embed the given minimal surface into R capital N. But this embedding condition exactly means exactly this Bolker condition. So we can just satisfy the Bolker condition by this F capital N Dirichlet data functions. So we restrict our data space to this G, which is our original W divided by this intersect with the span of this F1 to Fn. So this is just a ball in R capital N. So that is our data space at the moment. So with this minimal surface transformation becomes an analytic double vibration transformation, and we saw that it satisfies the Bolker condition. And we can use the FIO theory now. Okay, to go forward, we use this nice paper by Marco Mazzucchelli, Mikko Salo, and Leo Cho a few years back, which says that if you have an analytic double vibration transformation satisfy the Bolker condition, then it allows you to recover the analytic wavefront set in the following form. So if this transformation of a function beta is 0, it follows that the analytic wavefront set of beta intersected with the normal bundle of the minimal surface in our case is empty set. So how does that apply in our case? So we have two different assumptions in the injectivity of the minimal surface transformation. So the first one was this maybe easier one, which was this ampleness condition. So let's see how that works. So the ampleness condition means that you can probe the manifold into any direction by minimal surfaces. So it means that every x psi is in the conormal bundle of some minimal surface sigma. So now the above condition can be written as follows. So now the wavefront, analytic wavefront set of beta is exactly the same of analytic wavefront set of beta intersected with union of all conormal bundles over minimal surface. So this union here is just the full conormal space. So you just take the union outside, and then you have a union of empty set, which is empty set, which means that beta is analytic. As if beta was 0 outside of M, it follows that beta is 0 everywhere. The other condition was by foliations, and the argument there goes as follows. So if beta is not 0, I mean by assumption beta was 0 outside of the manifold, and we have foliation, it means that there must be a first leaf of this foliation where this beta becomes non-zero. That means there's a point in this first leaf, sigma s naught, x naught, such that the conormal at that point must live in the analytic wavefront set of beta. So this uses micro-local regularity fact. It's a little bit non-trivial, but it's true. So what this means is that we have this psi, which is now in the intersection of the analytic wave set of beta and the conformal boundary. But by this reason by Mazzucchelli, Sala, and Joe, this intersection must be empty. But now we saw that there's psi, so it must be that beta was actually 0 everywhere because we had a contradiction. Okay, I'm getting a little bit over time. I'm sorry. Okay, so just to get to the summary. So what did we do? So we studied this generalized boundary rigidity, and we saw that it actually works in a place between two classical inverse problems. So the earlier approaches were based on this Calderon problem, which recovered the manifold from the DMF of the minimal surface equation, and they relied on methods on the Calderon problem. And then today, we introduced this integral geometry approach, and there we reduced the problem to minimal surface transformation, and we were able to recover function from integrals over minimal surfaces. And we also saw that this integral geometry approach, a little bit like combines features from the PD theory itself as well, because we used this Runge approximation to verify the Boltzmann condition. So a little bit combines PD and integral geometry, which is quite nice. But there's still a lot of open question. How can you combine the best of these both worlds? So it's not at least clear to me what is the best approach to apply the best sides of these both problems, both approaches. So summary of the main results. So we studied the generalized boundary rigidity in conformal class. We were able to determine conformal factor from areas of minimal surfaces. And the very nice thing about this is that it worked in any dimension n2, and it provided Hölder stability for the recovery as well. The reason why it works is that it does not rely on solving the Calderon problem. It's mostly open in dimensions 3 and higher. It assumed analytic background metric and the sampliness condition. And sort of one reason why this works, in my opinion, is that this method, it actually enables the use of large variation through the sampliness condition. So why is that? So the sampliness condition meant that given a covector in the manifold, you should find a minimal surface that is normal to that one. So when you go through all these directions, through these covectors, you actually rotate the minimal surface sort of like in all directions. So you consider in these sampliness conditions large variations of minimal surface. So it probes the situation in many directions. So if you compare these results to earlier ones obtained by these PD methods, those recovered the metric from the DMF. They were SCCO 2D results due to the fact that they rely on the Calderon problem. They are best give logarithmic stability, and they work by small variations. So instead of having large variations, they only work with small variations of minimal surfaces. And then we also proved the injectivity of the minimal surface transformation under the ampleness of foliation condition. And we saw how to propagate micro-local injectivity, global injectivity. And we proved that this Boltzmann condition always holds when the dimension is at least 2 for the minimal surface. And here are some open problems. So here the background metric was analytic, so you can try to get rid of that one. We already considered the recovery in the conformal class. You can try to recover the metric itself as well, so full metric perturbations. In physics, the situation is in infinite spaces, so asymptotically hyperbolic settings. So what to do in the asymptotically hyperbolic geometries with this machinery, and also applications to specific physical geometries, so Schwarzschild ADS, Kerr ADS, those are rotating black holes, and also this ADS cross S5, which was in the original Rui-Takayanagi proposal that is open, I think. You can try that one. And also let me mention that this machinery might work also outside minimal surfaces. So the key which we saw is to verify the Boltzmann condition. So for example, you could try that in hybrid imaging models where you have slightly more data. You can also try this shape machinery in time-dependent equations, especially in the mean curvature flow. And I also know that some in our community have been interested in inverse problems for pseudo-holomorphic curves. And I think they have not worked out. So you can try these methods for these pseudo-holomorphic curves as well. And finally, what we actually did is that we considered, in a certain way, we considered the Calderon problem for a nonlinear anisotropic PD, and we were able to solve, even though the equation is anisotropic, the problem somehow. So the question is, can you apply these methods to other nonlinear PDs, maybe which are obtained by some variational principle by using this linearization to integral transformations. Here are the references. I will go back to those, but this is all. So thank you very much. Yeah, thank you.
Thank you very much, Tony, for the very interesting talk. Are there any questions or comments, please? Any questions or comments, please? Please feel free to unmute yourself.
I have a quick question. Hi, Tony. Nice talk.
Yeah, thanks very much.
Yeah, about the general linear recovery of metrics. Have you even tried linearizing? Is there a hope that this looks like an integral transform of something?
You mean this?
Yeah, full metric perturbations. Yeah.
Yes, right. Yeah, so we a little bit tried. So what you will encounter there is that sort of the microlocal machinery probably will work, but there will be gauges.
But the I see.
Yeah, but how do you?
But you get some kind of minimal transform of a tensor field or something?
Exactly. Yeah.
Okay.
Yeah, exactly. Yeah.
Yeah.
But there will be gauges. We tried it a little bit, but we were not able to solve the gauge problem.
Mm-hmm.
Yeah, but that's a very natural question to try.
Right. Thank you.
Yeah.
I have a question.
Yes.
So I'm a little bit confused by when you say that minimal surfaces satisfy Bolker's conditions somehow automatically. Did I understand it well? I mean, first, they don't even form a manifold, right? You have to restrict them to some submanifold. I mean, this is infinite dimensional manifold, roughly speaking. So you have to restrict them to some manifold.
Yes.
In order to have to parameterize them somehow. And is it true that somehow you can always arrange the Bolker condition?
Yes, that is what I tried to explain. So the Bolker condition follows from the Runge approximation for the linearized minimal surface equation. That's a very good question. So it was this slide here. Right. So injectivity of this left projection, it was the same as having V of x1 to be V of x2 for all Dirichlet data F. If x1 is not x2, then the Runge approximation says that we can separate these points x1 and x2, namely that this condition holds. So that is a contradiction.
Okay, but what is the statement then?
So we are proving the Bolker condition, which is the condition means that the left projection pi L is injective, and that it's also immersion, meaning that its differential is injective.
Well, okay, maybe we'll continue after that because I don't want to take the time from other participants.
Okay, yeah, but it's a very good question. And this is sort of, it was a little bit like a surprising fact here. We don't need to assume anything. It just works.
Mm-hmm.
Thank you very much. Are there any other questions or comments, please?
So, okay, so Tony, I have two questions, very elementary perhaps. So what if your metric is, I think what's called a scalar multiple of the Euclidean, like, sigma x times I? Is that known then, all these things?
I think even that is unknown. Well, now it's known, but even that was unknown.
Could you say that again?
Before these results, even that was, I think, unknown. So even if you have a conformal factor times some Euclidean metric,
But the factor is, so the Euclidean metric is analytic, I see.
Yeah.
So that's why it works. Okay, I see. Yeah. And the conformal factor doesn't have to be Euclidean, or, I mean, can be smooth, right?
Yes, that's of course, yeah. That's
correct.
not
okay.
Yeah.
Okay. I see. Okay. Now the second thing is, so your approach sort of sort of did injectivity for the the wavefronts, the analytic wavefront set, and then the analytic wavefront set sort of injectivity gave you the injectivity for the whole thing. So what that is, injectivity plays a serious role. Analyticity plays an important role there.
Yeah,
That would not be true for a smooth thing. So how do you see this method going forward for non-analytic backgrounds?
yeah. So this is sort of they need to do something different. So this sort of like completely analogous to the normal boundary rigidity. So there you can sort of do the similar type of things, but in fact, actually there you need to worry about these conjugate points. Here you don't. But for example, this paper by Plamen and Günther and Andras, they use these convex foliations to somehow deal with the situation. So that is sort of what one can hope to do here. If something in that direction.
Okay, so maybe just to understand this, so the convex foliation condition sort of carries over even for non-analytic backgrounds. Is that what you're saying?
Well, I don't. To be honest, in this setup, what does even convex foliation means? It's unclear.
Okay.
Because convex foliation is related to geodesics. But this
is related
convex
to?
foliation is related to geodesics.
Okay.
But there is no geodesics in this problem.
Oh, I see.
So what does convex foliation even mean? So you need to first try to think about what is a good like a replacement for the convex foliation, and then do something.
Okay. All right. Good. Okay. Thank you.
Thank you very much. Any other questions or comments, please?
Hi, Tony. It's Teemu here. So much for a fantastic talk and congratulations for a great result. This is very exciting. So can you explain a bit about this other condition? So ampleness, I understood very well. That's a very nice idea like this. But what was this like when you say you can foliate the manifold with minimal surfaces? This looks now something to me like you think about that you have like a set of minimal surfaces going through it, but like is there something else? So can you say a bit more about this foliation with minimal surfaces?
Yeah.
So what does it mean? Just define what do you mean by this foliation?
Foliation means in general that you have some kind of parameter, and then you have corresponding surfaces which foliate your manifold. So here in this slide, the parameter is sort of like S, and then this S parameterizes my foliation by minimal surfaces. Okay. So when I move this S, ultimately I have covered the full manifold. I'm now trying to find out what it is.
So you are basically just saying that this manifold M has to be like a union of this one-dimensional parameter of surfaces.
Yes, exactly. It is exactly that one. One way to think about it, consider that you have maximum principle. You just lift the boundary of the minimal surface. If you have maximum principle, this will actually foliate your manifold. So that's like a very simple way to do it.
Yeah, so it somehow seems that this latter condition is then way more general than the first one.
Yeah, but you cannot, at least I don't have an idea how can you use this foliation to prove the nonlinear problem. So this foliation condition was just for this injectivity of the minimal surface transform, which was the linearized problem.
I see.
So how the actual proof of the nonlinear problem works, as I shortly mentioned, is that you need to compute the symbol, or the principal part of the symbol of the normal operator of the minimal surface transformation. And you want to show that that is elliptic. The ellipticity exactly means that you can probe to all directions. So that means that you need to have this ampleness condition. So even if you have this foliation condition, this normal operator, at least I don't see it, how can you get it to be elliptic? And if you don't get it to elliptic, the argument fails.
Okay, thank you so much.
Yeah.
Thank you very much. Any other comments or questions, please?
Maybe just one quick question from Tony. Hi, Tony.
Hey, Ali.
So this is a slightly off the topic, but I wanted to know if the background metric is analytic. Would you be able to just use this area data to recover the metric? So this boundary determination, is this known for minimal surfaces, or is this a hard problem, easy problem? What do you think?
Boundary determination.
Boundary determination of the metric, like the jet of the metric from this area data.
That's, well, I guess nobody has done it because it's boring. But we did one example in this paper with Lauri and others. So then we got basically the conformal factor or something. But it's just like you need, why does for the boundary determination, you always have good solutions, regardless of the dimension, right? You just put like oscillating data on the boundary, then it will be like a decay exponential inside, and you use that for pick out the components. So you just, let's say you do this higher linearization method, then you can pick out the derivatives of the metric to any order you want by plugging in these suitable solutions to the integral identities which you obtain by linearizations. But that's a good project for some PhD student, not for us.
Thank you.
Yeah, thanks.
Thank you very much. Are there any other questions or comments, please? Any other questions or comments, please? If not, thank you very much, Tony, for the very nice talk. Thank you so much. Thank you very much, everyone, for coming. Thank you.
Yeah. Before we end, can I advertise this Leo's workshop? If somebody's still here. So there will be a workshop organized by Leo Zhou in Melbourne, and you can find the link to the workshop in the slides. So it will be of geometric physics and inverse problems. So there will be some experts from minimal surface theory, some physicists, and then people from our community in November this year.
Thank you very much, Tony. Thank you.
Yeah.
Thank you very much, everyone, for coming. Thank you.
Yes. Thank you very much.